Hello everyone. As part of learning big data using Hadoop and Spark, today we will be talking about Hadoop architecture. So why exactly did we go for Hadoop? The most prominent reasons being two. One, to store the huge amounts of data. The second one, to process the huge amounts of data. So the goal in designing Hadoop is to develop an inexpensive, reliable and scalable framework that stores and analyzes the big data. Whenever we are trying to work with the Hadoop, it always follows the classical master slave architecture. So wherein the master will have the complete control of the network or the system data, whatever we talk. So the master system will have complete control of the entire system, and the slave systems will be working on whatever instructions they are receiving from the master system. So Hadoop works on the classic master slave architecture for storing the huge amounts of data as well as for assigning tasks to the slave nodes. What are the slave nodes responsible for? They are responsible for storing the actual data as well as performing all the computations, processing, whatever is needed. So master nodes, what are they going to store? Slave nodes are storing the actual business data. Master nodes are responsible for storing the metadata and managing the resources, the resource information, the allocation of the resources. All such things are under the control of the master system. Now coming to the architecture of Hadoop, it majorly consists of three specific layers, starting with the storage layer, resource management layer, application layer. The storage layer, we also call it as HDFS, Hadoop Distributed File System. The resource management layer is taken care by Yarn, yet another resource negotiator, and application layer is done with MapReduce. So we will be talking in detail about each and every layer. Let us start with HDFS. The HDFS architecture, almost similar to Hadoop architecture, it also follows two types of nodes. Just in Hadoop we have master and slave. Similarly, HDFS has two types of nodes. One is the name node, the other one is data node. What exactly name node is doing? What exactly data node will contain? Name nodes will contain the entire metadata about a file. Say for example, I have stored a file, where it is located, into how many blocks the file is split, how many replicas of each block are there, where they are located, what is the size of each replica. All such information will be maintained by name node. So name node classically will maintain the metadata of the files which we are going to store in the cluster. The data nodes will contain the actual business data. Now I was talking about how the file will be split into blocks and distributed over the network. Let us see a simple example. Suppose there is a file of 612 MB. This file, if I want to store on a cluster, what will happen is the default block size in Hadoop or HDFS is 128 MB, which can be configured depending on the infrastructure you have. If we do not specify anything, the default block size is 128 MB. So if I have a file of 612 MB, the file will be broken down into blocks, 128, 128 and so on. There are 4 128, 512 plus the remaining 100, total 612. This is how the file will be split into 5 blocks, and the blocks will be spread across a network. This is how Hadoop stores huge amounts of files. Now, as I told, Hadoop HDFS maintains two types of nodes, name node and data node. This is how you can visualize. Name node consists of the metadata and data node consists of the actual amounts of data. And one more thing not to miss, name node runs on the master node and data nodes, they run on the slave machines. Coming to the application layer of Hadoop. The first layer is storage layer. We talked about HDFS, how it is storing the data, how it is splitting the data, all. Now coming to the processing layer of Hadoop, it is the MapReduce, wherein everything that happens to be on MapReduce is a key value pair. The input will be in the form of key value pair. The output from MapReduce is also in the form of key value pair. So basically the processing on MapReduce happens through key value pairs. Now, whenever we talk about MapReduce, there are two types of functions or tasks which the user is going to write. One is a map task, the other one is a reduce task, right? Say for example, my file is split into 3 splits. In this example you are seeing the file is split into 3 splits. 3 blocks. Split is nothing but the block. As I told, each block size is 128 MB. Say for example your file is broken down into 3 blocks or 3 splits. Then corresponding to that, it will define or it will take 3 copies of mapper functions or mapper tasks. So whenever you are trying to work with any file, the number of mapper tasks it replicates are equal to number of splits. Under every mapper the user writes a map function. Ultimately the user is going to write one mapper, one reducer. Depending on the number of splits, it automatically takes those many copies of mapper methods, mapper tasks. Now suppose my first split has 500 records. The map function will be replicated for every record. Please mind the calculations. Number of mapper tasks is equal to number of splits or number of blocks of the file. Number of map functions that will get executed simultaneously is equal to number of records in the entire file, right? So the first split has 500 records, second split has 500 records, the third one has 200. The total number of map function instances will be 1200. 500 plus 500 plus 200 equal to 1200. Fine. That is how it is achieving the faster execution, though the file is of huge size, because for every record we are giving an instance of map function, it is achieving faster execution. Now come back to MapReduce model. Suppose the file is split into blocks and the blocks each one is subjected to a mapper task. For every record you are trying to subject it to a map function which will try to identify what are the key value pairs which you are trying to expect in the output. Those key value pairs are extracted by each map function and those are given as the output from the map function. The map task takes out all your outputs and combines them and gives it to the next phase called reducer. So if you see, this will give you more clear picture. Suppose I have these are the file blocks. For every block there is a map method, mapper function. This mapper function will try to work on the number of records the blocks has, and the output from these mapper functions will be given to something called as combiner. Combiner is again a function which will try to combine all the outputs from these map methods according to the key value, and from the combiner the data will go to sort and shuffle phase. This will sort all the keys and the values corresponding to every key also. It will try to sort and shuffle. The output from sort and shuffle is fed to reduce method. Now ultimately combiner, sort and shuffle. If you try to talk about the output from the map function will be fed as input to reduce method. From the reduce method, the required output will come into picture. Now, the output from map methods, they are executing on multiple machines on the system. So, where do they write their output? The map functions will write their outputs on the local machines where they are executing. We call it as intermediate output. Once the combiner and sort and shuffle phase finish their work of sorting out the keys and values, they submit that to reducer. The reducer function will generate the required output. After the reducer has generated the output from reducer will be written on to HDFS and the intermediate outputs will be flushed out. This is very important for us because we are using the local memory, not to use it completely or not to exhaust the local memory. Once the reducer has generated the final output, the intermediate outputs on the local machines will be flushed out. So, in all these phases, whatever is coming as input is key value pair, whatever is coming as output is also key value pair only. Coming to the third layer or the intermediate layer, yarn, which is a resource negotiator, yet another resource negotiator, which works as the resource management layer in Hadoop. It started from Hadoop version 2 onwards. Now, yarn has three major components we need to talk about: resource manager, node manager, per application, application master. So, this application master is per application, whatever user task we are submitting, for every task there will be an application master. So, we need to talk about resource manager, node manager, per application, application master. Coming to, these are the, if you see the diagram, you can see there is one resource manager. For every node there is a node manager, and for every application we are submitting we have an application master. If you can see the diagram, one resource manager is there which is managing all the resources of the network or cluster. Number of nodes are there, those many node managers are there. In my example there are two applications, one is in green, one is in blue. So, corresponding to every application there is an application master. As the name suggests, resource manager, what does it do? It manages all the resources that are prevailing on the cluster, and it has two major components again. One is the scheduler, the other one is the application manager. What does the scheduler do? The scheduler gives resources to various applications which are requesting for resource allocation. It is a pure scheduler which will not track or monitor the execution status of the applications. It just allocates the resources. And also the scheduler does not guarantee the restarting of failed tasks. Due to some reason, suppose an application or a task failed in between, scheduler will not take care of restarting. Somebody else will do this job, we will see. And it just performs scheduling based on resource requirements. The mere job of scheduler is just to give the resource requirements which are submitted by the jobs. Coming to application manager, for every application there is a manager which tries to contact the per application master. Suppose there are 5 applications. For every application there will be a per application application master. This application manager will have a contact with the application master. In which container it is running, what are the resources it is using, how many more does it require or how many is it releasing, what is the status of its execution, everything will be taken care by the application manager. The per application application master is responsible for negotiating container. Container is the execution area where my task has to run from the scheduler. Node manager, for every node we have a manager. The node manager component, it runs on the slave nodes and it is responsible for holding the container for the task and monitoring machine resources. What are the resources the task is using, like how much CPU time it is using, memory, disk, all these things. Per application master, this is very important. This application master is a framework specific library. Depending on every application, what it has to do. It is responsible for negotiating resources. For doing this particular piece of task, what resources do I need? It has to prepare an execution plan, and that plan should be submitted to the application master, or it has to submit to the resource manager. The application master is the process which coordinates execution of an application in the cluster. This application master will contact all the containers. Suppose my task is broken down into 5 pieces and it is running on 5 machines in the network. It has to contact all those node managers where my task is getting executed. And it also has to take care of supplying the resources onto all those 5 nodes. And once the application master has started, it will periodically send a short message to the resource manager stating, I am alive, I am working, my status is this, I need these resources. It sends us small messages to the resource manager. These small messages are called as heartbeats, right? Then after it has prepared its execution plan, or we also call it as model of its requirements, the application master encodes the preferences and constraints in a heartbeat message and sends it to the resource manager. Once the resource manager receives heartbeat, it also responds through heartbeats. Whatever responses I am getting from the resource manager, the application master keeps on sending the status of the resource utilization. If at all I require any more, or if I am releasing some resources, those messages will be embedded into subsequent heartbeats. Depending on the containers we receive from the resource manager, the application master might need to update its execution plan. Say for example, I wanted 6 nodes and the resource manager has given us 7 nodes. So I got 1 extra. In such case, I will update my execution plan so that my task is broken down into 7 nodes instead of 6, right? Or I got only 3. I need to update my execution plan depending on how many nodes I am receiving. So depending on the containers it is receiving from the resource manager, the application master has to update its execution plan and execute the task. It has to take care of receiving of excess resources or lack of required resources. So the container allocation can happen dynamically once the execution has started. Say for example, I wanted 6 resources, I got only 3. I start working with 3. Once I receive extra resources, I keep updating the execution plan and execute. This is what the job of per application master. Thank you.